Welcome back. Now we are continue on session 2 of stellar evolution and the planet-star connections. The first speaker is Laura Rogers, and she will tell us about probing exoplanetary composition with white dwarf stars. Take away, Laura.
Awesome. Yeah. Hi. So I'm Laura Rogers. I'm a postdoc over at Noir Lab, and I'm going to talk to you about how we probe exoplanetary composition using white dwarf stars. And none of the work would be possible without all of my awesome collaborators who I've got listed at the bottom of the slide. So something that I guess keeps me up at night is trying to work out what exoplanets are made from. And if I had the most ideal scenario, I would be able to take a planet just like our Earth, I'd be able to stick it into a mass spectrometer, and out of it, I would get the exact composition of the planet that I put in. But we've been speaking a lot about saving money. You don't need to build a planet-sized mass spectrometer. You can actually use white dwarf stars to do this for you. But what is a white dwarf? So a white dwarf is a stellar remnant. So this is the core of a low-mass star that's left behind after stellar evolution. So our sun will turn into a white dwarf eventually. They're incredibly dense. They have a mass of about 0.6 solar masses packed into the radius of the Earth. And so this means that they have incredibly high surface gravities. And so because of this, you would expect to only see surface layers of either hydrogen or helium. And so here you can see the spectrum of Sirius B, which is the closest white dwarf to us. And you can see that there are only spectral features from hydrogen lines in this data. But actually, about 30% of the time, we do see additional metals in the spectra of these white dwarfs. And we call these polluted white dwarfs. And these elements are actually from planetary material. So there's a planetesimal, it gets chucked towards the white dwarf, and it gets accreted onto the atmosphere. And so if we take spectra of these white dwarf atmospheres, we can work out the bulk composition of the exoplanetary material accreted. Therefore, polluted white dwarfs are mass spectrometers for exoplanets. And we're doing a pretty good job, actually. So far, we've discovered 23 elements accreting onto white dwarfs. And a lot of the time, things seem to be pretty rocky, kind of dry, bulk Earth-like. And they have masses pretty similar to being consistent with asteroids in size. And a big aim of mine is to actually increase the number of white dwarfs where we have enough elements that we can actually study the composition and also the geology of the planetary material that's being accreted onto these white dwarfs. So I'm going to mention a few results from a couple of different papers that I've listed here. I can't tell you about them in detail, so please do go read them if you'd like to know more. So I'm going to show a few plots like this. On the y-axis, this is an element X normalized to silicon and then also normalized to solar, with the x-axis showing the different elements ordered in increasing condensation, increasing volatility or decreasing condensation temperature. So when I put data points on this plot, if you were to chuck something that was had a composition of the sun into a white dwarf, all of the data points would go exactly across at 0. Whereas if the white dwarf was accreting something that was more like bulk Earth, it actually would have a volatility trend. So you'd actually get a decrease as you get towards the more volatile elements. So here's the first example. So this white dwarf, I hope that you can see, is pretty consistent with being rocky. So your more refractory elements are consistent with solar and also bulk Earth. And then as you get more towards the volatile elements, you get this beautiful volatile depletion trend. So this is a nice, pretty rocky body that's been accreted by this white dwarf. And I'm showing you a couple of plots here. So these are abundance ratio plots. And I really wanted to try and put the white dwarfs into the context of the solar system. And so what we're showing in the background is a ton of different meteorites that we have in our solar system, as well as the sun and the Earth and chondrites. And then overplotted on the top are the white dwarfs. So we're looking at a lot of kind of key rocky species here. So we've got sodium to calcium versus magnesium to calcium, and then iron to aluminium versus silicon to aluminium. And the key really is that actually the accreted abundances, so this exoplanetary material, is pretty similar between these exoplanetary systems and also our solar system. So solar system materials, pretty common. So I mentioned a little bit about geology. And we can actually probe core mantle differentiation in exoplanetary systems. And we know that core mantle differentiation is really important because our Earth is differentiated, and without a core and a magma and a mantle, we wouldn't have recycling of elements, we wouldn't have this dynamo that's protecting us. So we know core mantle differentiation is important, but how common is it in exoplanetary systems? And going back to these plots, if we were to accrete something onto a white dwarf that was core-rich, you would see an enhancement in hydrophilic elements. So hydrophilic basically means like iron-loving. So these are the iron, chromium, and also nickel. But if you were accreting something that was more mantle-like, you would have a depletion in those elements. And surprise, we do actually find evidence of core mantle differentiation. And just to say, we can't tell the difference between an entire body that's been accreted or one that's differentiated where you accrete the whole body. So these are really fragments. So we're seeing a fragment of a mantle-rich body that's been accreted onto this white dwarf that you can see by this beautiful depletion in the hydrophiles, where you've got a very constraining limit of nickel and a low iron and a slightly depleted chromium. And then if we then compare again to our solar system, we're first going to focus on the left plot. So this is looking at iron to silicon versus magnesium to silicon. And iron to silicon can kind of be a proxy for your core mantle distribution. So things that have really high iron to silicon are probably quite core rich, and things that are low are quite mantle rich. And what's really cool is we find examples where we have core rich and mantle rich material accreting onto these white dwarfs. And when you start to get a really good buildup of elements, you can really understand the geology and the conditions under which core mantle differentiation happened. So for example, on the right, we're just looking at the hydrophilic elements. So we've got nickel to iron and chromium to iron. And again, these seem to have a similar spread to meteorites in our solar system. So it's actually really likely that the processes that are governing core formation are pretty universal across exoplanetary systems. And what about the volatiles? We love volatiles. Volatiles are really important. We need, we're mostly made of water. But what can we learn about volatiles in exoplanetary systems using polluted white dwarfs? So I've lumped these three white dwarfs together because they're actually pretty similar. So if we look at the more refractory elements on the left of the plot, these are all pretty consistent with being solar or bulk Earth-like. Whereas when you get more towards the volatiles, and specifically I want you to focus on the oxygen. So just to say, these are log plots. So the oxygen is actually almost an order of magnitude larger than you would expect for something rocky and bulk Earth-like. So they're pretty similar to being solar. And so we do a very simple thing where we do oxygen budgeting. So we put all of our different oxides together to form a rock and see if there's anything extra there. And we actually find that these are likely accreting water-rich planetesimals. And so finally, a little bit about carbon. So we don't have as many measurements of carbon in exoplanetary systems. We have less than 20 observations. But what I think this plot shows quite nicely is that we're again seeing a really large range of carbon across exoplanetary systems. And there's even examples by Xu of WD1425, which has a really high carbon consistent with Kuiper belt objects. And then we can take it just one step further and actually look at the carbon to oxygen ratio, which we know is really important for planet formation. If you have a really high carbon to oxygen ratio, then you're probably more likely to form carbides and potentially diamond planets compared to lower carbon to oxygen ratios. And we see a similar range to our solar system here, but ultimately we actually see nothing that has a solid supersolar carbon to oxygen ratio. So no diamond planets accreted by white dwarfs. Okay, so I hope that I've convinced you that that white dwarfs can act as a mass spectrometers for exoplanetary material, where we find examples of things being dry and rocky, but also things that are like water-rich systems and also core mass, the accretion of core or mass fragments. So yeah, there's really exciting stuff coming, and I'm happy to take any questions.
Great, questions? Okay, there's one question there in the back. And the second question here. So, okay, maybe John can go first. Yeah. Oh, Okay, 1, 2.
Okay, Finnegan Keller, ASU. Quick question. So with James Webb Cycle 4, there was a lot of interest in searching for white dwarf planets. Do we expect systems that might contain white dwarf planets to also be polluted, or are those sort of independent?
Yeah, that's a great question. And so with polluted white dwarfs, what we think we need is we need there to be planets that are destabilizing these planetesimal belts that have survived. And so the idea is that if you have a polluted white dwarf, most likely you have a planet as well. So yes is the answer.
Thanks. That was an excellent talk. Do you see evidence for time variability, and what are the time scales over which the, say, rocky element material kind of settles out and disappears? And yeah, and is it episodic that you see the accretion, or is it kind of more continuous?
That's a great question. So for hydrogen-dominated white dwarfs, the sinking times can be on the order of days. Whereas with helium-dominated white dwarfs, they're more like tens, hundreds, thousands of years. I have a few programs trying to look for variability, and the spoiler is that over 10 years, we don't see anything, even for these really hot DAs where you expect the settling time to be on the order of days. So we'll see. We'll keep monitoring them, and we'll let you know. Thanks.
Great. Okay, one last question.
Ilaria Pascucci, University of Arizona. Thank you very much. This was very, very interesting. So you said that you can exclude the diamond planets, right? But more recently, there have been ideas to interpret the mini Neptunes. They could be soot-like planets. So it would be very cool if you could place some constraints on that as well.
That's so true. Yeah, absolutely. And we should 100% do that. We've got a program where we're really expanding the number of carbon to oxygen measurements. I think we're going to double the sample size. So I think that's a great thing to compare to. Thanks.
In the interest of time, we have to move on. Let's thank Laura again.